Our second speaker this morning is James Saunderson. James Saunderson got his PhD from MIT, had postdocs at Caltech and the University of Washington, and has been at Monash University in the Department of Electrical and Computer Engineering. Monash is in Melbourne, for those of you who don't know it. I didn't know that myself. And he's going to talk about around the generalized lax conjecture. James.
Okay, thank you very much, Steve, for the introduction. And I want to make a big thank you to the organizers, in particular Melissa, but the organizers of this meeting for inviting me to speak here. It was kind of a surprise that I was asked to give this talk, and also for putting together what looks like a wonderful program for the week. Okay, so today, what I'd like to do in this talk is shine a light on what I think is a really nice open problem in an area of math that some people might call convex algebraic geometry. Okay, so I want to start with just contextualizing it around convex algebraic geometry before we get into talking about this problem. So what's convex algebraic geometry? It's in some ways the interplay between convexity ideas on the one hand and algebraic structure on the other hand for sets and functions that are defined by polynomial equations and polynomial inequalities. Okay, so I'm come really from a convex optimization background. All right, and a sort of a cartoon of kind of the interplay that that comes up in this area is the following. So imagine I start with something like a nice trigonometric space curve shown on the left in red. Okay, what convex geometers and convex optimization people love to do, we love to convexify things. So I want to take this space curve and I shrink wrap it to get the convex hull. And that's kind of often where our thinking starts and ends, and this is what our starting point for algorithms and other things. Once we got algebraic geometers into the picture, algebraic geometers told us, oh, okay, you should also zoom out a bit. You should think about the polynomials that vanish on the boundary of this object. And they gave us a whole lot of tools to start thinking about when we can and can't convexify objects efficiently and so on. So this area has sort of been developing over the last, I'd say, 15 years. And there's a really nice interplay of tools in both directions. So from optimization, that's kind of, I think there's been a flow of kind of algorithms and tools to real algebraic geometry to sort of give effective methods to study problems in real algebraic geometry. And in the other direction, I think the real algebraic geometry view has really given new ways to think about studying convex sets and convex optimization problems. So today, rather than looking at a topic that involves this interplay of tools, I'm actually going to talk about a topic where really we look at algebraic objects that come already packaged with really nice convex structure. So something that's really at the intersection of convexity and algebraic geometry. Okay, so for the plan for this talk is I'm going to spend about the first half of the talk, hopefully, introducing all the things we need to know to understand the statement of this generalized lax conjecture that was on the title slide. And then the second half of the talk, I want to give some number, not yet completely decided, of short vignettes, so short, sort of more recent research sort of pieces that are in some sense connected to the generalized lax conjecture. Okay. So let me introduce the main player of the talk. Okay. So the main player is a thing called a hyperbolic polynomial. Right? So to give the definition, we're going to start with a polynomial in n variables with real coefficients, and it's homogeneous of degree d. Okay? So that's one of the pieces, this polynomial. And the other thing is some point in Rn where this polynomial doesn't vanish. Okay? And we're going to say that the polynomial is hyperbolic with respect to this direction e if, when you look at this multivariate polynomial along any line in the e direction, so I get a bunch of univariate polynomials this way, if all of those univariate polynomials are real-rooted. Okay, so they only have real roots. So this is kind of this one way to say it. Let's now look at this, draw some pictures. We're going to mostly be working with pictures in this talk to represent polynomials. And so I want to show you firstly an example of something that is hyperbolic with respect to some direction. So I'm going to take this quadratic form in 3 variables, okay, with 1 positive eigenvalue and 2 negative eigenvalues. And I claim this is hyperbolic with respect to the vertical direction, for example. So why is that? If I draw any vertical line, so firstly in blue I've plotted the places, the real hypersurface where this polynomial vanishes. Okay? And if I draw any vertical line in this picture, it's going to hit that blue surface twice, as long as I count with multiplicity. The surface has degree 2. There's a polynomial of degree 2. So that's giving me my 2 real roots. There's no complex roots. Okay. It's going to be a lot easier for me and for you if we kind of dehomogenize the pictures mostly through this talk. So usually I'll be drawing pictures where I kind of like cut through this hypersurface somewhere, say like the vertical coordinate equals 1 picture here. And a slight reformulation of this definition would say that, in this affine picture, I'm hyperbolic with respect to E if every line that I draw that goes through E intersects the blue hypersurface, twice, degree number of times. Okay, so this is another way to see this. I'm not necessarily, if I'm hyperbolic with respect to one direction, I may not be hyperbolic with respect to every direction in the space. So for example, like the same polynomial, but a different point E, right? In this point over here, there are definitely some lines through E that don't meet this hypersurface where P vanishes, right? So these are situations where the univariate specialization has 2 complex conjugate roots and no real roots, right? So this is not a direction of hyperbolicity on the right, but the one in the middle is. So that's an example of something that is hyperbolic. For an example of something that's not hyperbolic with respect to any direction, consider replacing all the powers of 2 with powers of 4. Okay, so polynomial now form of degree 4. And if you think about any line in the space, it's only ever going to meet this hypersurface in at most 2 points. Right? So any of these univariate specializations have at most 2 real roots. They can never have 4 real roots. This is a degree 4 thing, so they're not real rooted in general. Okay, so this is an example of something that's not a hyperbolic polynomial. Okay, let's give a few more examples. So another really canonical sort of family of examples I get by taking a polynomial that's just the product of linear forms. Right, if I draw this hypersurface I get where this vanishes on a hyperplane arrangement defined by where each of these linear forms vanish. Okay, so for example, on the top left. And such polynomials are actually going to be hyperbolic with respect to any direction where the multivariate polynomial doesn't vanish. So any direction except on the boundary here is going to be a direction of hyperbolicity. Okay. Another kind of completely different place where hyperbolic polynomials tend to show up is actually a lot of them come from combinatorially defined polynomials. Okay, so to give a completely different example, suppose I take a graph with vertices and edges, and with each edge I'm going to associate a variable of my polynomial. Okay. Now what I'm going to do is I'm going to sum over all of the spanning trees in the graph. Okay, and for each spanning tree I'm going to write a monomial, which is the product of the edge variables associated with the edges in the spanning tree. So it turns out that this is also a hyperbolic polynomial. Okay, so somewhat different place this comes from. So I have asserted that's a hyperbolic polynomial. It's not at all obvious, unless you know why, that it is. So we need to think about what are some ways in which we can know that something is a hyperbolic polynomial. So how can I certify that something is a hyperbolic polynomial? Okay. So one way to do this is to write the polynomial in a way that makes its hyperbolicity sort of obvious. And one way to do this is to give what we call a definite determinantal representation of the polynomial. Okay, so I'm going to break this down. So what does that mean? That means I'm going to write my polynomial as a determinant of something. Okay, and this something is built out as follows. So I'm going to take n d by d symmetric matrices. So these are fixed, constant d by d symmetric matrices. Okay, I'm going to take the sum of ai times xi. Xi are my variables, they're scalars. So I get some symmetric matrix, the entries of which are all linear in the variables x1 up to xn. Okay, I'm going to write P as a determinant like this. So if I can do this, I'm well on the way to showing P as hyperbolic. But I need one more thing. I need to be able to have a definite determinant representation. I also need to find a point that when I look at its image under this map as a symmetric matrix, I get something positive definite, or without loss of generality, I get the identity matrix. Okay, so if I can write my polynomial in this form, no guarantees I can, but if I can, then I claim it's obvious that this polynomial is hyperbolic with respect to this special direction E. And the reason for this is a theorem we teach in linear algebra class, and that is that if I look at these univariate specializations of my polynomial, okay, what I'm actually getting is the characteristic polynomial of this symmetric matrix, where entries that are linear in X. Okay, and we all know that symmetric matrices only have real eigenvalues. Okay? And so this kind of theorem of linear algebra tells us that the polynomials I can form this way will be hyperbolic with respect to this direction E. Okay. So what are some places where hyperbolic polynomials arise? Okay, it turns out that, well, they kind of first identified, as far as I know, in the PDE literature. So hyperbolic PDEs are really, or at least linear constant coefficient hyperbolic PDEs are those where the symbol is a hyperbolic polynomial. Okay, and a lot of the early work in hyperbolic polynomials is really kind of done in this hyperbolic PDE literature. Okay, well, they turn up in a bunch of other places. So for example, in probability, sort of hyperbolic polynomials are lurking often when there's probability distributions that have negative dependence properties. The way I came to these is through convex optimization. So I haven't told you yet about the convexity side of the story, but hyperbolic polynomials will give us nice convex sets that are of interest in optimization. They show up a bunch in combinatorics, so a number of combinatorially defined polynomials have these hyperbolicity properties. Somewhat recently, the resolution of what was originally a problem in operator theory, this Caddis-Singer problem, somehow the final resolution of this involved real-rooted polynomials and their interlacing properties. This results of Marcus, Spielmann, and Srivastava. So kind of they're showing up here and there all over the place. So it's kind of interestingly not uncommon family of polynomials. I want to also mention some relatives of hyperbolic polynomials, some closer, some slightly more distant relatives that have also kind of show up in a bunch of places. So hyperbolic polynomials are very similar to things called real stable polynomials, which some of you may have heard of, and also Lie-Yang polynomials. So these are kind of different versions of multivariate polynomials with constraints on where they can vanish, okay, and are somewhat closely related. A bigger class that includes hyperbolic polynomials is a class that's got a lot of attention recently, is the class of what's called Lorentzian or completely log concave polynomials. So these have been kind of implicated, if you like, in resolving a number of really interesting kind of log concavity conjectures related to matroids and so on. So sort of some very interesting work, including some of the work of Peter Brandon and June He and Anari Liu of Eskaran and Vincent, have really used these to great effect to resolve a whole bunch of interesting problems lately. So Lorentzian's a bigger class than hyperbolic that's really good at proving log concavity statements. Okay. So those are hyperbolic polynomials. I've promised convexity, so let's see where the convexity comes in. So if we look at some of the examples we've seen already, what I want you to imagine doing is taking this blue hypersurface, this real hypersurface where the polynomial vanishes, and I want you to think about that as, the complement of that surface is dividing the space up into different regions. And it turns out that, at least in all the pictures I've shown you, the connected component that contains this direction of hyperbolicity is a convex set. Okay, so some pictures here. And it turns out that this is true in general. So we can define this set, which is the connected component where P doesn't, of the area where P doesn't vanish, that contains E, the direction of hyperbolicity. And it's a result, orbital guarding that this is a convex, this is actually a convex cone. Okay, convex cone, because these things were working in the homogeneous setting, when I dehomogenize, okay, we'll get these convex sets. And for me, throughout this talk, I'm going to call the hyperbolicity cone associated with the polynomial P and the direction E. I'm going to take the closure of this set, just because I prefer to work with the closed convex cone. Okay, so this is the main geometric player in the talk. All right, so we had this multivariate real-rootedness type properties on the polynomial, and somehow this gives us a nice convex set. So let me give you some examples of the kind of convex sets that come up from this construction. Right, so the most basic one is if I go back to my hyperbolic polynomial that's a product of linear forms. Okay? If I choose a point where all those linear forms take positive value, for example, all right, then the associated hyperbolicity cone is the polyhedral cone defined by this collection of linear inequalities. Okay? And so somehow if I dehomogenize and I get, I'll get a set that's a polyhedron, And from an optimizer's point of view, polyhedra are the feasible regions of linear programs. So linear programming is optimizing linear functions over polyhedra. Okay, so somehow they come out as kind of the simplest examples of this construction. The next family of examples I want to talk to play a big role in the next parts of the talk, so we're going to try to make sure I understand this. And these are a family of cones called spectrahedral cones. Okay? So if I start with a hyperbolic polynomial that has a definite determinantal representation, so where I kind of know I've got a certificate of its hyperbolicity of this determinantal form, and I take some point E where this sum of AI, EI is positive definite. Okay, we've agreed that's a hyperbolic polynomial. If you look at the corresponding hyperbolicity cone, what this is it's the intersection of the cone of D by D positive semidefinite matrices, okay, so symmetric matrices with non-negative eigenvalues, intersected with the linear space that's the span of these matrices A1 up to AN. So you can think about it as some cone coming from symmetric positive semidefinite matrices, some whatever it is, intersect with some linear space. Everything I can get that way, I'll call a spectrahedral cone. And it's the hyperbolicity cone associated with these things with a definite determinantal representation. Okay, so just to give you a concrete example, if you're struggling with the abstract formulation, the picture on the left is dehomogenized picture of the spectrahedral cone coming from this definite determinantal representation on the right. Okay, so I've got a determinant of a symmetric matrix that's linear in the variables x0 up to x3. It's hyperbolic with respect to the direction 1, 0, 0, 0, because that, when I plug it into the matrix, I get identity. Okay, and I get this beautiful thing that some people call the samosa, or the elliptope. And it's kind of as the associated hyperbolicity cone. Okay. So as an optimizer, why do I care about spectrahedral cones? Well, there's a family of optimization problems called semidefinite programs, okay, that are kind of a generalization of linear programs that involve optimizing linear functionals over these spectrahedral or over spectrahedra. Okay, so somehow this is a much more expressive class of convex sets. I can have things that are both got singularities, smooth bits, so much more general than polyhedra. And yet we still have kind of well-developed algorithms to solve these optimization problems. And they've had an impact on many, many different applications. I'll just put it that way. So sort of semi-definite programs show up somehow all over the place. And there's been a lot of study in the optimization community in kind of developing algorithms and theory for this class of optimization problems. Okay, so those are spectrahedral cones. Now we know all the things we know to start talking about sort of the original Lax conjecture and then soon this generalized Lax conjecture. So the original Lax conjecture, conjecture of Peter Lax, from the late 50s, is really a structure theorem for hyperbolic polynomials in 3 variables. So remember, we've already seen that if P has a definite determinantal representation, then it's hyperbolic. Okay, so that was kind of easy, that was linear algebra. So the conjecture is that the converse holds for hyperbolic polynomials in 3 variables. All right, so that's the conjecture. So that every 3-variable hyperbolic polynomial has a definite determinantal representation. So you can find 3 symmetric matrices, one of which is identity, and write this determinantal representation. And it turns out that nearly 50 years later, Bill Helton, who's here in the audience, and Victor Vinnikov actually proved this result. So it's now the Helton-Vinnikov theorem, that in fact every 3-dimensional, 3-variable hyperbolic polynomial does have a definite determinantal representation. And it's somewhat concrete, although the formulas, they give explicit formulas in the paper for these matrices, but they're a little bit complicated. They involve sort of theta functions, so it's not definitely quite an interesting and difficult result. Okay, so what are some implications? Well, at least in dimension 3, we can always certify hyperbolicity by exhibiting one of these definite determinantal representations. It also tells us that all hyperbolicity cones are actually spectrahedral cones. So they actually come as slices of the PSD cone. right? And so from an optimizer's point of view, that somehow you could think about hyperbolic programming being linear optimization over an affine slice of a hyperbolicity cone, that in 3 dimensions, that's no more expressive than semidefinite programming. Okay. All right. So that's the Lax conjecture. Let's try to generalize it. Let's be optimistic and think about, maybe something like this is true in higher dimensions. Okay, that's the spirit of the generalized Lax conjecture, and I want to go through some iterations to land on what the community has kind of seems to agree on should be called the generalized Lax conjecture. So the first thing we might try is we might just try, okay, well, maybe this is true in general. Maybe every hyperbolic polynomial has one of these definite determinantal representations. And this turns out to be kind of false and somewhat spectacularly false. So, and really a dimension count tells you this. So on the one hand, I haven't told you this, but there's really a lot of hyperbolic polynomials. So as a subset of homogeneous polynomials of degree d and n variables, hyperbolic polynomials have non-empty interior. Okay, they've got a full dimensional set. So there's a lot of them. Whereas if you really count the number of parameters in a definite determinantal representation with d by d matrices and n variables, it's just way, way, way smaller. So there's kind of no hope in general for something like this to be true. So okay, what's the next simplest thing we might hope for? We might hope that any hyperbolic polynomial, when raised to some power, has a definite determinantal representation. This kind of gets rid of the dimension counting issue, because by raising to some power, I allow myself to use much bigger matrices in the determinantal representation. Okay, so maybe I still have a hope. And it turns out that in certain cases, certainly the Helton and Vinnikov case, but perhaps the other really interesting case where this actually is true is if you look at hyperbolic polynomials in 4 variables of degree 3. Okay, it's actually true that the square of any such hyperbolic polynomial has a definite determinantal representation. Okay, so that's so it's true in that case, but it's known to be false in pretty much every other case of degree and number of variables, where essentially there have been explicit examples exhibited with proofs that that no power of them can have a definite determinantal representation. If you're looking for something to do in the rest of the talk, one of these cases is open. So, we're very interested in hearing from you if you've got a cubic hyperbolic polynomial in 5 variables, and you can show that no power of it has a definite determinantal representation. Okay, so that's an open question in terms of this second attempt at a generalization of the Lax conjecture. Okay. So this now brings us to what I think most people in the community who think about this stuff agree is what we're calling the generalized Lax conjecture. And this is actually just kind of, at least the cleanest statement of it is to free ourselves of the algebraic description and just ask that every hyperbolicity cone is a spectrohedral cone. So what does that mean? Every hyperbolicity cone can be realized as the intersection of the cone of some d by d positive semidefinite matrices, perhaps for some large d, intersected with a linear space. Okay? So we ask, does every hyperbolicity cone have such a representation? Okay. So you might wonder whether that's actually, how much more freedom have we given ourselves? And to try to understand how much freedom we've given ourselves, I want to give the equivalent sort of algebraic version of this conjecture. Okay. And the heart of the matter, which is meant to be illustrated in this picture on the bottom right, is that you can have many different hyperbolic polynomials that have the same hyperbolicity cone. Okay, so for example, I can take the hyperbolic polynomial, it's the product of these 5 linear forms and the hyperbolicity cone be the pentagon. But I could also multiply by some other factor, like this quadratic thing that makes the circle. It's a perfectly good hyperbolic polynomial, the product of the 2, right? But adding this extra factor didn't change the hyperbolicity cone. All right? So in particular, the hyperbolicity cone of the new factor contained the hyperbolicity cone of the old factor. When I multiply the 2 polynomials, it intersects the hyperbolicity cones, and so it didn't sort of make any difference. Right? So this is kind of the heart of the difference between our naive formulation of the generalized Lax conjecture and this one. Okay, so what's this equivalent algebraic version? It's asserting or hoping that it might be true that if P is hyperbolic, then there exists some other polynomial Q, so that P times Q has a definite determinantal representation, so has this nice description. Okay, so that already would certify hyperbolicity of P, okay, because if the product has real roots, then the factors will have to have real roots. But we want one more thing. We want also the hyperbolicity cone of this additional factor not to mess up our description of the hyperbolicity cone, okay? So it wants to be outside and not to change the hyperbolicity cone. Okay. All right, so it's fairly obvious that the algebraic version implies the geometric version, okay? It's a little bit more work, but not too hard, requires a little algebraic argument to show that the geometric version actually also implies the algebraic version, that these are actually equivalent statements. Okay. So let me say something about perhaps what I'd say is the most general results that are known related to this conjecture before I kind of move on to the second part of the talk. So the main sort of quite general results that are known related to this are valid for a subset, a big subset of hyperbolic polynomials that we call strictly hyperbolic polynomials. Okay, so what's the idea? The strictly hyperbolic polynomials are really just the interior of the set of hyperbolic polynomials. And these are the ones where if you look at all of these univariate specializations of your polynomial, they always have distinct real roots. Okay, so there's no multiplicity in the roots. So on the left, okay, you've got all these lines will intersect the hypersurface 3 times. It's a cubic curve. On the right, this particular line intersects only twice, and there's one of these roots has multiplicity 2 at the singularity. So this is not strictly hyperbolic because of that. Okay, and what you can maybe imagine from the picture is that strictly hyperbolic polynomials give rise to smooth hyperbolicity cones. Okay, so things are kind of somewhat nicer for these objects. Okay, so I want to mention two kind of, what I think of as significant results regarding strictly hyperbolic polynomials. So the first is a result of Mario Korma, okay, which kind of proves half of this generalized Lax conjecture for strictly hyperbolic polynomials. So what Mario's result says is that if you have a strictly hyperbolic polynomial P, you can find some thing Q to multiply it by so that the result has a definite determinantal representation. Right? So this tells us that we can certify the hyperbolicity of P, okay, using a definite determinantal representation. But what it doesn't do is it doesn't give us any control over the hyperbolicity cone. So we have no idea, I don't think, what the hyperbolicity cone of this factor that comes out, Q, is, and sort of what happens there. Okay, but sort of really amazing, really nice work. The other thing that's kind of known about these strictly hyperbolic polynomials, perhaps on the geometric side, is that the hyperbolicity cones of strictly hyperbolic polynomials are what we call spectrohedral shadows. So what we want in this generalized Lax conjecture is that the hyperbolicity cones are spectrohedra. They're slices of the PSD cone, of the positive semidefinite cone. Being a spectrohedral shadow is a weaker thing. So that's being the image of a spectrohedron under a linear map. Okay, so you shine a torch in your spectrohedron, you get a projection, and it turns out that's a strictly larger class of convex bodies, convex cones. Okay, so somehow, and in fact, this result of Tim Netzer and Roman Sanyol really leverages in a strong way work of, again, Bill Helton and Zhao Ni on sort of general results about representing convex semi-algebraic sets as spectrohedral shadows. All right, so that's the end of the sort of section on coming to the generalized Lax conjecture. What I want to do in the rest of the talk is, to give you 3 different, well, we'll see, 2 or 3, depending on the time, different kind of short stories related to, in a broad sense, related to this conjecture. The advantage of this is that, if you lose the thread of any of these, just wait 2 or 3 minutes, and hopefully you'll be able to catch up again. Okay. So for the first one is perhaps for the pessimists or the naysayers in the room. Okay, so we're going to look at some complexity issues related to hyperbolic polynomials. Okay, so if the generalized Lax conjecture were true, and we had one of these determinantal representations, kind of in general, how complicated might we expect these representations to be? That's the question. Right, so I want to start with another example of a hyperbolic polynomial, another beautiful one with, kind of coming from combinatorics. Okay, this is what is sometimes called the homogeneous multivariate matching polynomial. So again, start with your favorite graph, and we're going to sum over all the matchings in the graph. So matchings will be subgraphs where every vertex has degree 0 or degree 1. I'm going to sum over all the matchings, and for each matching, I'm going to build a monomial that keeps track of the edges in the graph, the edges in the matching, and the vertices not in the matching. Okay, so there's going to be two sets of variables, one for vertices, one for edges. Okay, build this thing. All right, and this turns out to be hyperbolic with respect to this particular direction, where I have the vertex variables be 1 and the edge variables be 0, for example. Okay, so it's a beautiful hyperbolic polynomial. It's in fact known that the hyperbolicity cone is spectrohedral. So Amini showed this in 2019. But one sort of challenging thing about this polynomial is that if you choose G to be the complete bipartite graph on n, n variables, on 2n variables, and you set the x variables to 0, this polynomial is the same as the permanent of sort of y, the square of the y variables. So why is this? Because if you set x to 0, you just look at perfect matchings in the graph, and perfect matchings somehow correspond to summing over perfect matching is really summing over, is really the permanent. So if you don't know what the permanent is, it's kind of the determinant without the signs. And it turns out the signs make determinant easy, and it's conjectured that the permanent is kind of difficult to compute. So more formally, like people who study circuit complexity, so this is some kind of model of complexity where you think about the complexity of building a circuit out of elementary arithmetic operations that will compute your polynomial. There's a sort of a big conjecture, which is kind of an analog of the P versus NP problem for circuit complexity, that says that unless this VP versus NP versus VNP, unless they're equal, whatever these are, it's expected that there's no polynomial-sized circuit that computes permanent. Okay, but there are polynomial-sized circuits to compute determinant. So kind of if we had a, what am I trying to say, a small determinantal description for this polynomial, that would mean you could have a small circuit to compute permanence. So we don't expect this to happen. Right? And this is really an observation of Oliveira. Okay. So yeah, on the one hand, so already hyperbolic polynomials, they might be sort of quite difficult to compute, and sort of any determinantal representation will have to know how to compute, somehow know how to compute the hyperbolic polynomial. Another kind of similarly mildly depressing thing is that hyperbolicity in general can be difficult to check, right? So to check hyperbolicity, I need to check every univariate, so every one of these univariate specializations and check that it's real-rooted. There's a lot of those. And it turns out that this is hard in some formal complexity theoretic sense to check, to verify that even a cubic polynomial is hyperbolic with respect to some given direction. Right, so that's the statement. And again, just to give you another crazy example of a hyperbolic polynomial, so again, take your favorite graph, and what we're going to do is build we're going to sum over the edges and multiply, two vertex variables, xi and xj together, and an edge variable yij to make some cubic. Right, and if I add a bit of extra stuff to this thing, it gives me a polynomial in, multivariate polynomial. And what I've got here is this polynomial is parametrized by some integer k. So this first coefficient somehow depends on this integer k. And it turns out this polynomial is hyperbolic with respect to the first coordinate direction if and only if the largest clique in the graph you built this from has size at most k. All right, so somehow finding the largest clique in the graph is one of these classic hard combinatorial optimization problems, and you can somehow encode that problem inside the testing of hyperbolicity of this polynomial. Okay, so somehow, like, again, if I had a definite determinantal representation with this as a factor, I'd be able to, that would certify hyperbolicity for me. And so that determinantal representation has to know about solving, the maximum clique problem for this graph. Okay, it doesn't mean it's impossible to have, it just means that I don't think there's any hope for a generic description of a definite determinantal representation to be simple or concise in any way. It should likely be quite complicated. Okay. So now perhaps we're, feeling pessimistic about the generalized lax conjecture after those observations. So if we're feeling pessimistic, maybe we want to think about trying to disprove the generalized lax conjecture. One strategy we could take is we could sort of take a convex geometric point of view, and we could say, well, if the generalized lax conjecture were true, then any property that spectrohedral cones have, any kind of geometric property they have, hyperbolicity cones should also have those. Conversely, if I can find some weird geometric property that spectrohedral cones have, and show that hyperbolicity cones don't have this in general, that would disprove this conjecture. Okay, and so the kinds of things that we've studied along this line is to look at the facial structure and the boundary properties of spectrohedra and hyperbolicity cones. Okay, so a reminder, or if you've never seen this before, kind of ignore the formal definition. A face of a convex set is some kind of natural notion of a convex substructure in the convex set. Okay, so in this picture, all of the red shaded bits are faces of the respective convex sets. So they come some kind of boundary objects that are also convex. Okay. Among faces, we can classify them. One of the many classifications we could make is that we could say a face is either facially exposed or it's not facially exposed. Okay, so a face is facially exposed if you can describe it as the intersection of the convex set with a supporting hyperplane. So if you can kind of isolate that face with a supporting hyperplane. So all the faces in the top picture are actually facially exposed. You can imagine a hyperplane that just chops off that face. But actually there's pretty innocuous looking convex sets that are not facially exposed. So an example on the far left is this, you take the circle and a point outside it and you take the convex hull. This has two non-exposed faces, it turns out. So it's not a given that a convex set is facially exposed. And there's, in fact, a whole lot of strengthenings of the idea of being facially exposed that you may or may not have as a convex set. Another kind of geometric notion for convex sets is the notion of a tangent cone. So if I take a point on the boundary of my convex set, I can look at all of the directions that I can move infinitesimally in and stay in the convex set. And if I take the closure, I get a thing called the tangent cone at that point. Okay. So if we think about spectrohedra, it turns out the following facts are kind of have been known for a while, is that faces of spectrohedral cones are again spectrohedral cones. Tangent cones of spectrohedral cones are again spectrohedral cones. And spectrohedral cones have a property called being amenable, which is a strict strengthening of being facially exposed. And this amenability has nothing to do with amenable groups, just one of these terminology things. Okay, so the actual question is, do hyperbolicity cones enjoy similar properties? Right? And the answer is, okay, yes. So what might we hope to prove? Okay, so it turns out that the faces of hyperbolicity cones are hyperbolicity cones. Okay, that tangent cones of hyperbolicity cones are again hyperbolicity cones, and that hyperbolicity cones have this amenability property. All right. Okay, so I don't want to tell you about the proof, but I want to tell you about one ingredient in the proof, because it's the sort of thing that you would never imagine to do, just not in your craziest dreams, unless you are thinking about these objects really as hyperbolic polynomials and thinking about polynomials. Okay, so the key tool here is that you can start with any hyperbolic polynomial in a direction of hyperbolicity, and if you take the directional derivative, which will produce a multivariate polynomial of degree 1 smaller, in that direction, it turns out that's again a hyperbolic polynomial. And this is easy to prove. It's really like essentially the fact that the roots of the derivative interlace the roots of a polynomial. Okay. So if you do that for, say, this hyperbolic polynomial defining the boundary of the hexagon on the left, if I do this once, the resulting hyperbolic polynomial will vanish on this crazy orange curve. If I do it again, the resulting hyperbolic polynomial will vanish on this green curve. So you get these really, really interesting convex sets and polynomials just from this fairly innocuous operation. And another thing that happens is that every time you differentiate, the hyperbolicity cone gets bigger. Okay, so this is why these are sometimes called derivative relaxations, because things get bigger. And they're often called Renegard derivatives because Jim Renegard did a whole lot of really interesting work on this operation in the context of optimization over the years. Okay. So if I zoom in a bit on this picture, it turns out that you can represent any face of a hyperbolicity cone as the intersection of some linear space with a sufficient, after taking sufficiently many derivatives, with a linear space in such a way that the linear space goes through the interior of the cone. And this allows you to get an explicit description as a hyperbolicity cone. Okay, so that's sort of the picture for faces. Somehow this observation was key to the results we have on facial structure of hyperbolicity cones. For tangent cones, well, it turns out you can also take the derivative in boundary directions of the hyperbolicity cone, and you still get a hyperbolic polynomial. The hyperbolicity cone still gets bigger. And what's amazing about this is when you do this, it preserves the local geometry at the point where you take the derivative. So I've taken the derivative in the direction of u here, and the stuff locally around u stays the same, and things change sort of far away. And if you do this enough times, you get down to the tangent cone. Okay, so this is kind of why tangent cones of hyperbolicity cones are hyperbolicity cones. Okay. All right, so for our last vignette, we failed to disprove the Lax conjecture through geometry. So maybe we'll just consider some really nice hyperbolic polynomials and see if it's possible to construct explicit spectrohedral descriptions for their hyperbolicity cones. So some very symmetric hyperbolic polynomials. So one way I can build very symmetric hyperbolic polynomials is to start with a permutation invariant, so a symmetric hyperbolic polynomial. Okay. Right, so let's say I start with one of those. The simplest of these might be to take the n variables and just take the product of the variables. Okay. What I can then do is I can build a new thing that turns out to be a hyperbolic polynomial by taking where the variables are a symmetric matrix. Okay, so what I'm going to do is I'm going to take the eigenvalues of my symmetric matrix and plug them into my symmetric polynomial. Okay? So if I took the product of the variables, when I plug in eigenvalues, that will give me the product of the eigenvalues, which will give me the determinant. Okay. So I can do this when I start with any symmetric hyperbolic polynomial, and what I get is a new hyperbolic polynomial that's hyperbolic with respect to the identity direction. And instead of being symmetric in the sense of being permutation invariant, it's now going to be symmetric in the sense that it's invariant under conjugation by orthogonal matrices. Okay, because it only depends on the eigenvalues of the thing you plug in. Right, so one nice example of this is to take the elementary symmetric polynomial of degree d in n variables. This turns out to be a hyperbolic polynomial that's symmetric. And if you do the kind of spectral version of this hyperbolic polynomial, what you get is, in fact, the sum of the d by d principal minors of your n by n symmetric matrix. Okay, this is also a hyperbolic polynomial. All right. This is a way to build beautiful symmetric examples of these objects. And so you could then ask, well, if I build things this way, do I get things that satisfy the conclusion of this generalized Lax conjecture? Right, so what's the simplest maybe setup we could start with is to take any linear form and then symmetrize it. So take all the permutations of the coordinates and build a product of linear forms this way to get a permutation invariant polyhedral cone. Okay. And then ask for the set of symmetric matrices with eigenvalues in this polyhedral cone. Right, so this is some crazy, beautiful but crazy convex set that I'll call a spectral polyhedral cone. Okay, the result, joint work with Roman Sanyol, is that spectral polyhedral cones are spectrohedra. Okay, so these are hyperbolicity cones, and they do satisfy this conclusion of the generalized Lax conjecture. I'm not really going to say how we do this, but suffice to say that you do need some multipliers for this to work. And essentially, we construct some linear map that takes in a symmetric matrix and produces a really big symmetric matrix where the eigenvalues somehow have all the inequalities we want as eigenvalues, plus some other junk, and the other junk doesn't mess up the hyperbolicity cone. So maybe just by good grace, more than anything else. So another thing we can do is we can start with instead of a permutation invariant polyhedral cone, I could start with a permutation invariant spectrahedral cone, so something again with a concrete description. And then I could look at the set of symmetric matrices with eigenvalues in this thing. Okay, so it's a bigger class. And the question in this direction, also an excellent tongue twister to finish the talk on, is are spectrahedral cones spectrahedral? Okay, that's kind of, yeah. So the answer is we don't know in general, but the previous slide gave an answer for some class of examples. And another, again, nice piece of work by Mario Kuma shows that the answer is yes, under some representation theoretic assumption on the linear map that defines the spectrahedral cone you started with. Let me just say it that way. But in particular, one of the examples you get out of Mario's construction is that this hyperbolicity cone of the sum of the d by d principal minors, this is spectrahedral. Okay. All right, so to wrap up, what have we seen? We've seen hyperbolic polynomials, lovely algebraic object. These are multivariate polynomials with certain strong real-rootedness properties. These are certainly very special objects, but they're not completely uncommon. They arise around the traps. And certainly, if you see one in your mathematical life and you can recognize it, which is not a given, then you know that you have all these nice convexity properties and other things that you might be able to exploit in your work. The generalized Lax conjecture is, in a sense, a structure theorem or structure conjecture about the structure of hyperbolicity cones. I think I have no idea if it's going to turn out to be true or false, or we'll never know. I would say that, so certainly if it's true, we have a beautiful structure theorem. If it's false, then whatever those counterexamples are will teach us something about why hyperbolicity cones are more expressive than spectrahedral cones, and that would be very interesting as well. All right, so I'd like to finish by thanking some of the collaborators that I've done work on in this space with, and thanking you all very much for your attention today.
Once again, let me ask for any questions, and if anybody has any questions, please use the microphone that's circulating around the room. Anybody? Anybody from the overflow room? Oh, here's one.
Making it work.
Thanks very much. If I understand this correctly, it's very hard to construct the Q that you need in the P times Q, or did I miss something there?
Yeah, I think it's not. I think in the examples where we know how to do this, it's usually that we get a determinant or representation where you somehow know P is a factor, and then Q is the rest of the stuff.
So you do it the other way around?
Usually, what seems to be going on when things work is that you do it the other way around, and then you try to check that the Q doesn't change the cone. Yeah, but I don't think we have a good systematic way to think about how to construct the Qs. People have tried things like powers of linear forms and so on, and there are also examples that show that's not enough somehow.
And that's not necessarily unique either. You can have different ones, or?
I guess you can definitely have different representations that will give you different Qs. There may be a unique minimum one, but I'm not convinced about this either.
So you're basically not too interested in the Q, you're more interested in the determinantal representation?
I mean, I think for me, I'm mostly interested in the representation of the cone, which kind of then pushes the Q out of the picture, but I think it probably depends. Someone with a different view might have a different answer to that question.
Thanks very much.
Yeah, thanks.
Further questions?
So you had a few examples with graphs, and I think one of the first examples was with this polynomial related to the spanning trees of a graph.
Yep.
Is it obvious why this has the hyperbolic property?
Excellent. I was meant to make the comment as to why that's true, and I forgot to do it. So the reason is really this, if you've heard of it, this matrix tree theorem, that if you write a version of that where you put edge weights, if you get the determinant of this kind of edge-weighted Laplacian, this essentially gives you the spanning tree polynomial.
So does that give you the definite determinantal representation for that polynomial?
Yeah, I mean, if you use the reducible Laplacian, so you kill the kind of redundant row that you need to do, then this gives you a definite determinantal representation, yeah.
And one more maybe weirder question is, I think the original theorem you stated for Lux is that it's true in 3 dimensions, right?
That's the theorem.
Yeah, that's the theorem.
The Helton and Vinnikov theorem.
So is there like a specific geometric/algebraic property in 3 dimensions that you exploit for that to be true?
I'm going to refer that question
to the
to
authors.
Bill Helton to ask to answer in the break, but yeah, I'm not sure. I think so. No, okay.
No?
Or no to answering the question, one or the other.
Okay, thank you.
All right, thanks.
Can I see another hand up there? Anybody from the overflow room have a question? Okay. I see one.
You're required to wait, I believe. So.
So do I understand it correct that you don't ask the question about 2 because it's a product of linears?
About 2 variables. Yeah, exactly. So that's also a good question to help people understand. If you've got a form in 2 variables, it's kind of secretly univariate. If it's real-rooted, it's really just a product of linear forms, and that's all that can happen in 2 dimensions. So it's true, but not so interesting exactly.
Anybody else? Okay, let's thank James once again.
Thanks, Steve.
All right, just a quick administrative announcement. Just a reminder that the sessions start at 2 p.m. Many of the sessions are in this building, and we have other clusters over in the science building and the engineering building. There are a number of maps online, but watch out for the people with blue name tags.